In this video, we're going to discuss graphing polynomials and the characteristics that we need to understand what a graph of polynomial function will look like. So first, let's define a polynomial in one variable. If it is a polynomial of one variable, it would be in the following form, where a sub n times x to the n power plus a sub n minus 1 times x to the n minus 1 plus all the way down to a constant. I know this form probably looks a little complicated to you. If it does, don't worry, I'll give you some more concrete examples so you understand what a polynomial of one variable would look like. The second rule, the coefficient of our first term here, a sub n, cannot be a 0. All the other terms have to be real numbers. So we cannot throw complex numbers in as coefficients for it to be polynomial. The third rule, n is a non-negative integer, so we will not have any negative exponents. If we have a negative exponent, then it is not a polynomial. The next thing that we will use is how do we write a polynomial in its standard form? To write it in standard form, we will take all the terms and we're going to write in descending order from the highest exponent down to the smallest exponent. On top of that, once we have it in order from the highest exponent down to the smallest exponent, another way to think of this is that you have it from its largest degree down to the smallest degree, then we can call that coefficient in front of the largest degree the leading coefficient. So here are some concrete examples. We have several different types of polynomials. We're going to start with a constant polynomial. A constant would just be any number that you could think of. We need to know what the degree of any constant polynomial is. Well, even though you do not see a variable here, you could think of this as 12x to the 0 power. Now it does have an exponent, which will tell you what the degree is. So the degree of this is 0. If I throw that x to the 0 back in there, the leading coefficient then would be the number in front of the variable, which happens to be 12. So 12 would be my leading coefficient. Next we have a linear type polynomial. An example would be 4x minus 9. There's only one variable, so the largest exponent would be the 1 that's with the x. So its degree is 1. The leading coefficient, the number in front of that x, which is 4. Now we have a quadratic polynomial. We see that the largest exponent of this expression here would be the second power, so its degree would be 2. And then the leading coefficient is the number in front of the variable of that largest power, so 5. The final example of a polynomial that we have here has a name for it, is called a cubic, which the largest exponent is 3, so its degree would be 3. And then the number in front of the variable, 8, would be a leading coefficient for this particular polynomial. So if you get homework problems, the directions will say, state the degree and the leading coefficient of each polynomial in one variable. If it is not a polynomial in one variable, you need to explain why. Well, first example, 8x to the 5th minus 4x cubed plus 2x minus x minus 3. I double check a couple things. First, do I have only one letter, one variable in the problem? These are all x's, so we're good there. Second, are the exponents, or the degrees, are they in order from the largest down to the smallest? Check the exponents here. We have 5, 3, 2, first power, and then no power, so they are in order. So then the 5 that I have highlighted here would be considered the degree of the polynomial. And the leading coefficient, jump to the number in front of the variable, that would be 8. Another example, 12x squared minus 3xy plus 8x. What should jump out to you is that we have two different letters here. That's multiple variables. So this would not be a polynomial of one variable. And the reasoning, we have multiplication of x and y. And a final example, 3x to the 4th plus 6x cubed minus 4x to the 8th plus 2x. You should see that, well, we got all x's here, so that is one variable. The variables are going 4 down to 3, back up to 8, so it is not in its standard form. So I rearrange all of these terms so that it is in its standard form. This will tell me my degree is then going to be an 8. The leading coefficient then would be the negative 4 in front. So a question that you may have is, what's the importance of a degree and what's the importance of the leading coefficient? Turns out these two numbers will tell us the shape of it will tell us the shape of all polynomial functions or polynomials in general. And polynomial functions only behave in 4 very distinct ways, and I'm going to go over the 4 here. The first one we're going to look at is what are all the different combinations of a degree and a leading coefficient. We're going to say, well, what happens if the degree is an even number and the leading coefficient in front of the variable is just a positive number? What will happen is that the arrows in the ends, no matter how far out on the x that we go positively or how far out on the x that we go negatively, the arrows will always end up going up and up. So we have to describe the end behavior out of this. And you may remember the end behavior like this. As x approaches infinity. So let me remind you this. This right here, as x approaches infinity, we're talking about when we look to the right side of the graph. Is the arrow going up or down? The arrow's going up. That's up in the positive direction, so that's why we say that f of x is going to positive infinity. Then we jump down to the other part. As x goes to negative infinity, I'm talking about the left side of the graph here. Is the arrow going up or down? We see that this is going up, so that's why we say positive infinity. So the other combination that we would have here is what if the degree stays even, but the leading coefficient goes from positive to negative? What the graph will do then, the arrows are now going to go down and down. So we describe its end behavior. As x goes to infinity, instead of f of x going up, it is now going down. That's towards negative infinity. So we say f of x goes to negative infinity. We look to the left side of the graph. As x goes to negative infinity, then the arrow once again is going down to negative infinity. And just to make another connection, no matter how large your even degree gets and how small that negative leading coefficient is, the graph might do a lot of crazy things in between, but in the end, all these graphs will behave the same. So let's switch up the degree. Let's go to odd degree now and have a positive leading coefficient. All of your graphs will behave this way. So we describe its end behavior. As x goes to positive infinity, so I'm looking to the right, f of x stays positive, it's going up. As x goes to negative infinity, we look to the left, the arrow is going down, so f of x will go to negative infinity. A way I like to think about this is, I think of slope-intercept form. You know, slope-intercept form, positive slopes go up from left to right. That's what its degree and what its leading coefficient would be for all those types of slope-intercept form equations. The last combination that we will look at is the degree stays odd and the leading coefficient goes to negative. So that flips the graph. So the arrow goes up on the left side, down on the right side. So its end behavior, we'll say as x goes to positive infinity, f of x then is going down to negative infinity. On the left side, as x goes to negative infinity, f of x is going to go up to positive infinity. So there's your 4 different types of end behaviors that you'll have for all polynomial functions. Let's use this to our advantage. Okay. And a key concept that goes with this. Odd degree functions will always have a minimum of one real zero. And just to remind you, a real zero is just an x-intercept. Where does it cross the x-axis at? However, even degree functions may have any number of real number of zeros, or they may not even have any at all. It may not cross the x-axis anytime. Here's some examples. In red, I have even degree polynomials. And I know they're even because the arrows are both going in the exact same directions in the end. The first example, notice that the red does not cross the white x-axis at all, so there are no real zeros. If you look at the second example, we have it crossing once, twice, a third, and a fourth time, so that would be 4 real zeros. Jumping over to the odd degree polynomials, we have arrow going down on the left side and arrow going up on the right side, so we know for a fact that it is odd, and we count the times that it hits the x-axis. There's twice and a third time, so we have 3 real zeros. And the final one, it only crosses it once, so it's guaranteed to have at least 1 real zero. Alright, so homework type problems that you have. You're going to be given a graph. You have to tell 3 things. Describe the end behavior, so that's with the arrows and the infinity symbols. Determine whether it's an odd degree or an even degree, and then finally tell me how many real zeros it's going to have. Here's one example. I'm going to do the middle bullet point first. I think it's easier to point out if it's even or odd first. Arrows are both going in the exact same direction, so that fits the definition of an even degree polynomial. Describe the end behavior. Well, we look to the right as x goes to positive infinity. Ask yourself, is the arrow going up or down? We are going down, so we will say f of x goes to negative infinity. Next, look to the left as x goes to negative infinity. Up or down for the arrow, it is going down once again. So f of x goes to negative infinity. Last piece, how many times does this graph hit the x-axis? Hits it once. It hits it twice, so we have 2 real zeros. Another example. Looking at the graph, where are the arrows going? Are they in the same direction or are they in the opposite direction? We see here the arrows going up on the left, going down on the right, so that is definitely an odd degree polynomial. What is the end behavior? We look to the right as x goes to positive infinity, the arrow is going down, so we go down to negative infinity. Look to the left as x goes to negative infinity, this time the arrow is going up, so that is positive infinity. And then finally, how many times does the graph hit the x-axis? And we count. 1, 2, 3, 4, and 5. So this graph would have 5 real zeros. And there's the use of degrees, how to find a degree and its leading coefficient, and then what the degree and the leading coefficient can tell you about the